Hello and welcome back to Calculus 3. My voice is not back yet, so stay close, right? The lecture is on lines and curves in space. We want to define the way to trace the position in 3D. So when you draw a graph, let's say y equal x squared, you can regard that graph as a position graph, let's say in time, where the particle moves along that path. The question is, how do I describe a straight line in space, or how do I describe this line in space, right? If this line is a path of, let's say, a fly buzzing around. So also a straight line which could be oriented in any way on the in space. So what do we do, or how do we get those equations so that we can do more math later on? Well, we start first with the concept of a vector valued function. So vector valued function will simply be a vector that consists of functions which portray the position in space. So vector valued function, we generally use R, and we say R of t is going to be f of t, g of t, and h of t. Because generally we trace the position in time. So this would be the vector valued function, and this is the definition. Now what this actually is the vector that consists of three functions, and these functions are parametric equations. So the reason why there is a chapter 10 homework open for you as a review is for you to review and practice parametrization. Parametrization is very important throughout the entire Calculus 3, and if you're not able to do parametric equations, you are pretty much done with Calc 3. So let's talk about that. Let's review parametrization so that we can go on with the course. So parametrization, which is chapter 10, lecture 10.1 in your textbook. We teach that in this school in Calculus 2. Set of parametric equations break dimensions apart in respect to a parameter, let's say parameter t for time, or theta for the angle, or you can come up with other parameters as well. We will see the arc length parameter and so on. So you can take your function y equals f of x from pre-calculus and break it into x equals g of t and y equals h of t. So you can take a function and break it into this set of two parametric equations, each of which is a function. Now that's not very efficient, but It's useful here and there. The one that we actually care about a lot is the one where you take an equation that it's not a function. And because it's not a function, you cannot use calculus on it because you differentiate a function, you integrate a function. If you have an expression that it's not a function, what you can do, we write it explicitly as f of xy, like this, equal to 0. Equation of the circle would be a good example, or ellipse. That can be also broken into x dimension and the y dimension, and now you gain a lot because each of these is a function. So what we have over here is a way to take something that it's not a function, therefore not compatible with calculus, and convert that into parametric equations, which are functions actually, but it's a set of functions, and then deal with calculus in that way. In some certain cases, this is a lifesaver for our calculations. So here is an example. If you have equation for a circle, now this is something that you memorize. There are proofs to show that this is correct, but you learn the initial state and then you fix it later. So your equation x squared plus y squared equals to, let's say, 16 is equation for a circle of radius 4. So you have a circle, and the radius of that circle is 4. It is centered at the origin because there are no minus 0 or minus 1 or minus whatever on its x's and y's. And the parametrization for this is given by x equals 4 cosine t. You can also use theta. And y equals to 4 sine t, where t is between 0 and 2 pi to trace the entire circle. So this is the set of parametric equations, and then your parameter t goes from 0 to 2 pi. So we have this as our equations for a circle. Now note that you went from something that is not a function, right, because it has a y squared and the Thales vertical line test, to a set of two equations which are functions, because we know that sine, cosine are functions. So we gained the sum of the functionality, right? And now we can use calculus easier because we have functions. Now, with parametrization, we get a lot of other cool things. One of those things would be the orientation of the graph. See, you are starting with two variables, x and y, 2 dimensions. But over here, you are ending up with 3. When you have an extra variable or a parameter, well, you have additional degree of freedom to actually have something else introduced. For parametric equations, that manifests as the orientation of the motion of the curve. You see, when you start at t equals to 0, the first point that will be traced on the graph as you start tracing this around would be the point 4, 0. So your circle begins there. Note that when I drew the circle, I started here, right? That's where I started drawing the circle, and I went around, right? So you have the place where you start and the place where you end as you draw the circle. Motion for me to draw the circle was this way. Well, that's exactly what parametric equations do. They give you this extra degree of freedom, except they start drawing the circle like that. So this is t equals 0. This position here is t equals pi over 2. This over here is t equals to pi. This is t equals to 3 pi over 2. And finally end with t equals 2 pi, which ends at 0. This gives us the orientation counterclockwise. So, counterclockwise orientation. When x equals r cosine theta or t, let's put t, and y equal r sine t. Now I will tell you that you can also have a clockwise orientation, clockwise, when x equals r sine t and y equals r cosine t. So either way, you are going to have a circle with radius 4, whether you use cosine sine or sine cosine. The only thing that switches when you swap these is the orientation, whether you go clockwise or counterclockwise. Standard motion is counterclockwise. Your positive angles go counterclockwise, everything is counterclockwise as a standard, but you can reverse it, and in some cases we will have to reverse it, so you need to know both. So this is what parametric equations do. They take your functions or non-functions and break those dimensions apart. Now that we are moving to 3D, we are going to have 3 of these, x, y, and z, and then the parameter. So technically 4. They are all oriented as well. Now, if I want to use the language of what we just did, I can write this circle as the vector valued function for cosine t for sine t. So now you see that the vector valued function is just a new name, a new label from what you know from before. If you know how to parametricize, you already have parametric equations. All you need to do is to write those parametric equations in a vector, and there you go. You have your vector valued function. So vector valued functions are just a collection of parametric equations, right? And they describe the path. So now, as we move along, I am going to have some kind of a line in my XYZ 3D system. It doesn't matter what kind of squiggle you post. Just remember, right? Here it is. Right? That's it. So what I'm going to do now is I'm going to define a vector R which is going to trace this line. So let's put a bug on this path, and this bug is gonna go bzzz, right? Going this way, 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 right? So you have a bug. The way we trace this bug is with a vector from the origin. Let's do blue. This vector is going to reach every point of the line, and this vector is your vector R, which is f of t, g of t, h of t. So what I have now Let's do an example. So say that r, vector r of t is given as t squared plus 1, e to the t, and 1 over t plus 1. So example, right? I can ask, what is the initial point of the bug? Initial point, t equals 0. That's going to be r of 0. When you plug 0 everywhere, you get 1, 1, 1. Vector 1, 1, 1 has as a terminal point, point 1, 1, 1. So the location of the bug is at 1, 1, 1 at time 0. How about 2 seconds into the flight? Well, that's t equals to 2. You are calculating r of 2, which would be 5 e squared and 1/3. This is a location in space where the bug is 2 seconds into the flight. Well, this is a vector whose terminal point looks like that with parentheses. So you first calculate the vector because you have vector valued function. And then, yes, the point would be, oh, I can write the point. Here, point in space. Would be 1, 1, 1. Point in space. 5 e squared 1/3. It's important to know that this is a vector and this is a point. You have the spiky brackets and you have a parentheses. So make sure you make those don't want to forget that. The next so now with this we are able to trace the position of anything in space, right? Now in Euclidean space, the first line that we want to describe and understand is the straight line, linear line. So let's talk about linear line in 3D, in R3. A linear line must have again parametric equations in terms of vector valued function. Let's draw the linear line in 3D space and derive the equation from there. If you are honors option, you are responsible for this derivation. It could be on the test. So here is the line L that I want to observe and define. We know that line in space, no matter what dimension you're talking about, is defined by 2 points. So we need 2 points. And one of these points needs to be the initial point. So we'll call this P0 with the coordinates x0, y0, and z0. And guys, this is a fixed point. Then we have another point P, which is going to be the second point, and that point will have the coordinates x, y, and z. Now let's bend your mind a little bit. Every single point along this black line is a point P, and that's the point P0. So you can draw this point P anywhere on the line, because the coordinates of the point P are x, y, and z, which are all of these points. So any combination of x, y, and z that will keep you on the line will give you point P. Point P0 is the fixed point. That's the point that you are going to get. Point like 2, -1, and 7, right? So if I say find the line going to 2, -1, 7, 2, -1, 7 is this one, the fixed point. Point P will always have x, y, and z, and that's all of the other points on the line. So now what I'm going to do is I'm going to do a simple vector addition. I'm going to stretch a vector from, and let's not be dramatic, let's do the. So I'm going to stretch this vector, and I'll call it vector R0, because that is the terminal point, is the fixed point with x0, y0, z0, so it makes sense to call it R0. And then I'm going to have this green vector here, P0, vector P0P. That's the green vector. And finally, I am going to have the resultant vector. When I add these two vectors, I get vector R. So if we follow vector addition, I am going to write that vector R is equal to vector P0P times parameter T, I'll have to explain that later, plus R0. So these are the first things that we have to do. Now please note that all of these vectors are given to you. We know that vector R has coordinates x, y, and z, because it stretches from the origin to x, y, z point. We know that R0 has x0, y0, z0 as the coordinates. And then finally, we are going to call this vector V, which is the P0P vector. We'll have the coordinates, well, we have to subtract, right? We have to go and say x minus x0, comma, y minus y0, comma, z minus z0. Now, why am I choosing vector v? It's actually a velocity vector. And we are multiplying it by time to get the distance, because you are adding r and r0. Those are distances. So p0, p needs to be also a distance vector because the position from p0 to p changes in time. So it's a little bit tricky there, but we have this times t over here. So now this turns into an equation r is equal to vt plus r0. I hope you are seeing y equal mx plus b over here. That's exactly what you need to see. Y equals mx plus b. So I'll write it in blue. Y equals mx plus b. This is the multivariable analog of y equal mx plus b equation. And when I say multivariable, I don't mean Calc3 or 3D. I mean 17 dimensions or 135 dimensions. This equation works in any dimension because it's a vector equation. What I'm going to do is I'm going to say, okay, I need this in 5D. Sure. You have x, y, z, w, and q. Well, I don't know what your fifth dimension is. So this equation is the straight line in any dimension. If you just say, can I have this in 2D? Sure, plug your y and x and y in and you have it in your 2D world. So this is any dimension here. But in Calc3 we are dealing with third-dimensional space. Therefore, I am going to expand this using third-dimensional vectors. So I am going to write these. So I'm just plugging in now. I know that r is x, y, z. I know that vector v is x minus x0, y minus y0, z minus z0 times t. And I know that this is x0, y0, z0. All of those are given here, right? So you have them. We'll just plug them in. Now, you can write the vector as a row vector, or you can write it as a column vector as well. So let's stack them. X, y, z is equal to x minus x0, y minus y0, z minus z0 times t plus x0, y0, z0. And finally, we can write the set of parametric equations for a straight line. Read the first row. Oh, I also want to, let me just define this as ABC. So A is x minus x0, B is y minus y0, and C is z minus z0. So it's easier to write these things. So now I have x, y, z equals ABC t plus x0, y0, z0. So finally, x is x0 plus at, y is y0 plus bt, and z is z0 plus ct. And that is the set of parametric equations for the line in R3, 3D. We can also write this as R of t is equal to x0 at, comma y0 bt, comma z0 plus ct. This is three equations that you always must show, all three. Three equations which are describing a straight line in 3D realm. Obviously, each one of these is linear line, and when you combine three of them at the same time through parameter t, let's say time, then you get the line that is slanted in space. So now, how do I figure out this line in space? This is 4 feet or 3 feet. Is half of me? That's half of me, right? No, it's not. It's a 4 feet cable. So this cable is 4 feet, right? How do I describe this in space? Well, I need to have a location of this point and a location of this point, right? And I can calculate those because I have grid in 3D. Calculate x, calculate y, calculate z, and you will have endpoints. When you have endpoints, you can go and compute the rest. Now, it's very important to pick one point to be your fixed point, because the other one is the floating one, right? So let's go. Find the equation of the line given 1, 3, 6, given endpoints 1, 3, 6 and -2, 5 and 4, whatever. You are given 2 points in space, and you will pick one of these 2 points to be your fixed point. So let's say fixed right there. Now if that's fixed, that's immediately your P0, which is x0, y0, z0, and that's the one, guys, that shows up in your end equation. So now, what do I do? Well, I need vector v, and vector v is P0P. Well, that's your P. So you can calculate the vector v by saying -2 minus 1, 5 minus 3, 6 minus 4, for a total of -3, 2, 2. This is your ABC. And all you need to do now is just to write the equation of the line. I hope you see that this is much faster than your algebra way where you had to find the slope and stuff.
Shouldn't the 4 come first before the 6? Because isn't the 4, isn't the 6 the next point?
Oh, yes, 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 yes. It's 4 minus 6. That's a negative 2 there. Nice catch. So now, x, y, and z, we put our fixed point 136 minus 3t plus 2t minus 2t. These are your ABCs. So this is your P0, this is your vector v, and this is your t. This is the answer, guys. Who would say that figuring out the line in 3D would be much faster than figuring it in 2D, right? We never had to compute the slope. Vector v that you get by simple subtraction of 2 points acts as a pro-dimensional slope, right? So remember, vector v, the green vector v, has the same orientation as your line. So which way you slant the line, that's the way that vector v slants, right? So your vector v acts as a throw-dimensional slope of the line. And you get it by simply subtracting p minus p0, each coordinate. Now, obviously, you're supposed to do it correctly. Don't do what I do what I say, what he says. Right? Yes?
So then, using t, do we use the interval 0 to 2 pi, or is it more?
That's only when you have the, that's only when you have circle. Now, over here, you are going to limit your, remember, this line is infinite. The way I have it here, and I didn't specify any limitations on t, this line is infinite. Now, your question is, can we limit t? And the answer is yes, because as you can see, this line is finite, right, in length. So, if I limit my t to go from, let's say, 0 to 3, then I just need to write that, well, that's the next concept here. We're talking about the line segment now. So if you are dealing with the line segment, and we are going to need line segments, especially in chapter 14, for line integrals, the line segment will be the equation of the line, and then you will have to chop that t interval to get the line segment. So you will have to integrate over the line that goes from 0, 0 to 5, 5. You have to do this problem first, and then put your t to go from 0 to 1, and then you have your line segment. Then you can go and do problem from chapter 14. So all of this work that now is a full problem will be something that you do in a margin in 2 seconds, so that you can set up for the chapter 14 problem. So now the next talk here is exactly your question, line segments. Line segments. So to get a line segment, we limit the parameter. We'll limit the parameter. So what do? We say t is going to be in between two values. Now those two values in chapter 14 will become limits of your integration on a definite integral. It will be an integral a to b, and those would be your a and b. Now these a and b are not to be confused with a, b, c from vector v. So let me put that also in parentheses over here. These are not AB from V equals ABC, just to make sure that you don't confuse those. So to get a line segment, we are going to limit the parameter t. Now, to go back to the equation of the circle, let's say that for equation of the circle, you only want half of the circle, but it's this half. And we will eventually want this. So say this is what you need from a circle. Your parametric equations are still going to be the same. If the radius is 4, you still have r equals 4 cosine t, x equals 4 cosine t, and y equals 4 sine t. But now, since you do not want the full circle, you have exactly what you want there, and you know that your t equals 0 is here, and t equals pi over 2 on top, then this one better be t equals negative pi over 2. So your t for this particular picture is from negative pi over 2 to positive pi over 2. So this is the full parametrization when you include this. So let me write that in blood. Must be included with equations. It's not there for decoration. It cuts the exact part of the circle that you need. Again, chapter 14, integration, the line integrals. You are integrating over this curve. You have to parametricize the curve, and you have to provide this. Parametrization will be used within the integral. These guys become the limits of integration. So it's not there for decoration, right? You will be using this. Therefore, if you are using the full circle, you don't have to specify the limits. You can, 0 to 2 pi, full circle, done. But then you can keep tracing over the circle, and that's fine. 2. Straight lines are all infinite, because t goes from negative infinity to positive infinity, unless you cut that to the size that you need for the problem or your design. So if you say that you are designing something that has to be 4 feet long, you have to make sure that your parametrization, that your parameter t allows for the 4 feet long chord. That's longer. That's 7 or 8 or 9. Eight or 9. So that's line segments. Infinite line, no information on t given. Therefore, t is infinite. Therefore, this line goes forever in both directions. Over here, to find the part of the line, so line segments, part of the line. Right? That's what it means. And that's that. So now, curves in space. Meaning R3. Well, those are described by the vector valued function. Very important part, they are oriented. Because the extra parameter gives extra degree of freedom, which manifests as orientation of the curve. What does that mean for our reality? Well, the car drives on the surface. The road could be described as a parabola that sits on the floor. Now, if that's the road, and the car loses control going into the curve, let's say here, the car will continue to move in the tangential way, which means it will, if it loses the grip, let's say you have some leaves on the rain, right? The water, the friction between the tire and the road is gone and the car slips. The car will continue tangentially off the road. Now the same thing will happen if you now take this, which was on the floor, and you straighten it up and you make a roller coaster which derails at this position here. The car will be launched in tangential motion. If you are to take the roller coaster situation and overlay that on the road, you will find that the angle at which the car flew off the road and the angle at which the car was launched because it derailed is exactly the same. It doesn't matter whether it stands up or on the side. It's the same path that the unfortunate object is going to take. So the orientation of the parametric curve tells us which way this will go, because remember, there is this as well. So now, if the car is moving to the left, it's the left vector that gives the motion. But if the car moves to the right, it's the right one. So, if I say that the motion is blue, then it's the blue tangent. And if the motion is red, it's the red tangent. So the curves are oriented, and that will help with the tangent line to tell you which way the object goes. These portray velocity, obviously. So now, let's talk about Helix. If you ever disassembled a pen, you found a little spring inside. That spring is a helix. domain is a circle. So if you are to look at the little spring, oh, actually, here, I can take this notebook. Here's your helix. This is what the helix is. This is spiral or a spring, right? Now, if you look at this spring this way, you all see a circle, right? It's a circle here. When you look at it sideways, you see this gradual rise up. So now, the domain is a circle. And we know that the equation for this line, if it's oriented counterclockwise, is x equals r cosine t, comma, no, and then y equal r sine t. So now what is the equation for the circle, for the helix? Well, two dimensions are already given. That's your domain. So r cosine t and r sine t, which is what gives us the circular base. And now you observe the rise. If I put a constant there, that means all you have is the ring, because if the z coordinate of the helix is, let's say, 5, that means that you have a ring at 5 feet elevation. And it's the end of the story. There's no spiral, there's nothing is moving up and down, because your z coordinate is just 5. So if that third coordinate there is constant, all you're getting is a ring. You're getting a circle at elevation z equals 5. If I put a linear term there, then the rise is linear. The spiral in this notebook has a very shallow angle. So I might want to have over here p over 15 or whatever, right? To have a slow rise. If I have a large number, you know what happens with the slope with a large number. This is your zero slope. This is your 45-degree slope of 1. So 0, 1, infinite. So halfway at 45 degrees is where slope of 1 is. So your helix would be rising at 45 degrees like this if you have just t. If you want a slow rise, you are going to have this as t over 10, t over 15, t over 20, and it will be a slow rise up. Do you have to put t there or a linear? No. You can put quadratic, exponential, you can put whatever you want. That will make your helix progressively go faster. Remember that the spring from your pen is not, it's not actually just this helix. It has the sides that are clumped together, right? And then there is a spiral. So the notebook here is a perfect helix. That was awesome, right? But if you actually have a spring, The spring, when you look at it on the side, it's very busy, and then it has like that, and then it's very busy, right? So this would be piecewise, because these stacks over here are a very shallow slopes, and in the middle, maybe t over 2. But I can put t squared. T squared is going to start coiling slow and then go whee. Exponential function will do even worse, right? Coil slow, coil slow, coil slow, and then shoot up. You can put any function, or you can make a slinky by putting in sine in there. You know the slinky that you play with, right? So if you take the slinky and you connect, you get the coil in a circle. And oh, actually, I think they have it in the book. Let me see. Yeah, there it is. So if you have your sines and cosines in a base, that will, the sine and cosine in a base give you the tube of the slinky, and then the extra trig function connects that slinky into a donut shape. So you have a donut shape which is made out of slinky. There's a mathematical equation for that. So please, when someone brings up in a conversation, what do you know? I know equation of slinky. What do you know? Yeah. Now it's done. That's why no one talks to me. Or they're very careful when they do. So observe that you have your cosine and your sine for your x and a y, which gives you the base of a slinky, a circle, and there's another sine which wraps it around into a donut, and you have that shape. So now you let the particle in your accelerator move that way. You let the bug fly that way, and you understand mathematically, and you can build machines and things. Yes?
So t isn't the height, t is the slope between each.
Very good question. T is not the height. Think of the x, y, and z positions within that vector. That's what you're supposed to think of. So in the example which I gave you, z coordinate had t, and the helix was wrapping around t. I'm going to switch things now. So your question was, is t the height? No. T is the way in which the shape progresses in z direction. What I'm going to do now is I am going to say r equals vector r cosine t, r sine t. Note that the t is in a y position, therefore clear? So you can wrap around x, wrap around y, wrap around z. The position in which t is the axis you're wrapping around. T shows how fast you are wrapping. So if you put t, or 10t, or t squared, or e to the t, right? You start slow and you shoot. If it's linear t, it's always constant. You put sine, you bring the slinky together into a circle.
So t is the point on the axis. As you plug it in, so it's like t over 2, and then at y is equal to 1, it would be 1/2. So you wrap around in the half.
Yes. Yes. So that's why it's important to actually do these graphs by hand at home to actually get the hang of how these things work. Play with basics. You try to go and do the diabolical homework problem and get stuck on it for 1 hour, well, it's because you didn't clear the basics. The basics. You haven't seen this before, so what are you going to do? Hopefully, you are going to create this. Wait, did you say you had the Oculus?
Yeah.
Yeah. So just go into the desktop mode, take a spray, and just go, right? You will create a helix around you. And when you look at it, right, the way you stand in the middle of it, right, you stand in the middle of that spray, it creates the spiral around you. Each point in space is defined with the coordinates. So if you're standing in 0, 0, your spray is going to start there, right? So for t equals 0, it's going to be a point on the graph. And then from there, as it progresses in time, it's going to go up. You can trace every single location by computing the time. Time equals 0, time equals... Now, good times to use are actually pi's because of the circular base. But the first example that I did at the beginning of the lecture did not have circular base. Now, can you graph something like this by hand? Yeah. It's going to take a very long time, but yeah. I did this. What are you going to do? You're going to graph it for t equals 0, t equals a half, t equals a 1, t equals 1.5, equals to 2, and then you are going to get the points in space. This is why I asked about, if you have Oculus Rift, you can actually do that in virtual reality, and you can create the graph in 3D, which you can walk around, which is amazing. We don't have those toys here in the classroom. So you have to play on a 2D paper if you don't have Oculus at home. Or whatever other. Well, little disclaimer, what I'm doing now is I'm creating a 3D environment in which you can do these graphs in 3D, but they will be pre-made because you all have smartphones. You go on Amazon and you buy the enclosure for virtual reality, which is $6. You put your phone in the thing and you run the app on the phone. There's already a lot of material on YouTube, 360 videos to play with this, and $6 is a worldwide investment already, because YouTube has the videos that you can use to observe the environment. So let me just find the shark one. I like the shark 360. So when you get one of these 360 videos on the phone, by buying the $5-6 enclosure, it's waiting for the commercial too. All right, you will have the little icon. You have a little icon over here that will split it for the virtual reality set. If you don't have the virtual reality set, you use the I just gotta go back now. You use this, but look, the way you turn the phone, it turns the picture around. So the camera stands still, and the phone tells you where to look. You can look below, up, because it records 360 degrees all around you, everywhere. Now, if you have the goggles and you put this in, right, and you do the split, $6 only. They have thousands of these videos already on. You can have a completely different reality of what the video looks like. Now, Oculus is $400. Still, the amount of time that you would use it for is practically free in comparison to movies or any other type of entertainment, especially if you're wasting $100 and $150 to go and see a concert, which is, in my opinion, my humble opinion, insane to waste that much money to go see a monkey jump for 2 minutes on the stage. Anyway, the next, so as you are learning these things, if you haven't done this before, do the most mundane, simple things first to get used to the 3D environment and the graphs and things, and then try to do some of the crazy stuff. So make sure that your first problem is not a slinky that bends onto itself with the three trig functions inside the vector valued function. Play with lines. What you can do, you can stretch a piece of the rope. This is one of the project problems sometimes. Stretch a piece of the rope, tie it to a door handle and a bed, right? Use your 3D environment in the room to find the endpoints of the rope. Take pictures of everything. These are what the project problems are. Take pictures of everything. Find the endpoint of the rope. Find the other endpoint of the rope by measuring feet, right, with the measuring tape. And those are the points in space. Find the equation of the line segment. Find the length of the line using the distance formula. And then measure the rope. Make sure those numbers are the same. Otherwise, quit your engineering. And I'm serious about it. Because if you're not able to do these kind of things, what illusions do you have that you are doing as an engineer? Like, what is your job? Someone tells you, oh, I'm an engineer, I don't use math. That person works sales for an engineering company with engineering degree, because the engineering of that person is terrible and the company can't use it. So when you go to the interview, they will ask you the actual questions from your class, from the things that you learn. And if you don't know them, you still might get employed, but department to department, you're eventually going to end up working sales. So great, $80,000 student loans because you didn't do the clubs and organizations and things. You have to take loans. $80,000 of loans, and now you're working sales for the rest of the life because you haven't learned anything. So the project is defined and designed for you to actually bring reality to these things. One of the project questions is to boil an egg first, so you don't break it along the way. Trace that egg on the paper, figure out its volume using triple and double integrals, and then do the water displacement on the egg to measure the volume, and then when you measure the volume, how well the volume that you calculated correlates with the one that you measured in the cup. And then you can ask yourself, oh, actually, is that cup okay? Then you might take it to the chemistry lab and use one of the super duper precise measuring beakers and things to measure the volume, and then see how well your calculations and modeling, because that's what engineering is. You take a look at something, you create mathematical model for it, and when you have mathematical model for it, you can machine those things and make those things and adjust them and tweak them until they are perfect and able to be used. You don't eye things in engineering. The way the card is designed is you hire this artist who makes nice smooth curves on the car, and then engineer comes in and says, now I got to move this back because it's not aerodynamic. The car is already terrible efficiency. If I keep the mirror right here, it's going to make it even worse. And then the artist goes, yeah, but this guy calculated stuff. So your job is to be that person who calculates things and understands how to link the 3D reality with mathematical equations so that you can actually build stuff that works. And that's what the project will be all about. So the easiest thing that you can do is just stretch a little piece of rope or something, or a cord, extension cord, I don't care what it is, in a house, and spend 30 minutes measuring and these things so you can actually come up with the line segment and the equation. And that's exactly what the outcome of today's lecture is on lines and curves in space. Once you clear the linear lines, then you upgrade to the spatial curves. Then you can analyze the flights and things because let's see, because this, right? Do you think that they have Joe sitting somewhere tracing how these things work? Here's the North United States. These are the current flights that are happening in 3D. Do you think that you have someone in the control tower figuring out how two planes are going to miss each other? You have thousands of planes in the air at any given time. Your job as a computer scientist is to have the mathematical models in your head so you can write a software that will efficiently make sense out of this thing. Otherwise, every other plane will collide, trying to land and so on. This is not done by hand. Your computer science job is to trace these airplanes in a 3D. You have the XY position above the ground and the altitude on Z. Great, X, Y, and Z positioning, no problem, right? But then you have to add the curvature of the Earth to the whole thing, because on the planet, which is curved, because it's a ball, the straight lines are longer paths to take because of the curvature. You take the curved path along the geodesic, so the path is shorter. So on the surface of the planet, curved lines are shorter distance-wise than the straight lines. Yeah. So you're not used to that. But you can practice that as well if you draw on your basketball a little bit. So these are the things that we use the lines and curves in space for. And as you observe the intercontinental travel over here, you see, to get from London to Canada, you are not flying straight, because you're going to run out of fuel and you're going to die. Because this is much longer than this. So you will see the streams of planes doing that. So when someone tells you that Earth is flat, it's worthwhile considering sitting 20 years in prison. Yeah. Because we get to clear that as far as possible. Make sense? There you go. So that's your lines and curves in space.